let's recall what we did last time in the end. So I was talking about variations of Hodge structures. Z variations of Hodge structures. So the setting was as follows. We had the complex manifold B as a base. We had a local system over B. So let's denote it like this. So this is a local system with fiber that are some finite rank, free abelian group, and then we had Hodge structures on the fibers varying holomorphically. So we define the corresponding vector bundle. So this is VB tensor product with the structure shift. So this is a holomorphic vector bundle. And then we have the Hodge filtration. So let's say that our Hodge structures will be of weight k. And then we have a filtration by holomorphic subbundles. They are decreasing, yes, so the last one is Fk V, and then up to F0. Well, let's just say for simplicity that the weight is positive, then like this. So this is V. And then also there was this condition. So this is just a bundle with a flat connection and with a flag of subbundles. But the important condition is that we have Griffith's transversality. So let's recall this. So we have this flat connection, the Gauss-Manning connection. Induced by the local system. So that the sections of this local system are flat, and the Griffith's transversality condition is that nabla of FPV is contained in Fp minus 1. Yeah, so this connection applied to the section of this subbundle will not give the section of the same subbundle, but will somehow increase the Hodge, so this index, or decrease this index by at most 1. Okay, and also we always consider polarized variations of Hodge structures, so we have a polarization. Polarization is given by non-degenerate pairing. Yeah, so we have this morphism of local systems such that for every fiber psi t defines a polarization on the fiber. Yeah, so this fiber carries a Hodge structure, yeah, so given by this filtration. And it is polarized by the non-degenerate pairing psi. So what I also defined was the this is so let's recall what it means that it polarizes here, because I'll use this. This psi is a non-degenerate form. It will be so -1 to the k symmetric. Psi is skew symmetric for odd k and symmetric for even k. So we have about the Hodge structure, we think in terms of the representation of the lintors. And we have the veil operator. And so then if we write down this form Q, which is just psi twisted by the veil operator, then Q is positive on the corresponding real vector space. And then there was the Hodge locus. So the Hodge locus. So how do we define it? So let's recall that we have now the total space of our vector bundle V. So to define the Hodge locus, so let's recall first how to define the locus where this V itself has more Hodge classes than in the general point. So let's assume that V is of even weight. Yeah? So if we want to consider Hodge classes, we should look at the points of this abelian group that are also of type PP or KK. So let's assume that the weight is even, equal to K now. Yeah? So Hodge classes in the fiber over the point T is the same thing as so the X in this VBT is a Hodge class. If and only if it belongs to FKV, yeah? At the same time, so that just FKV intersected with VBT. So we look at this intersection of the somehow integral classes and this component of the Hodge filtration. So we have the total space of our vector bundle V, and inside of it we have the total space of our local system. So this total space is, it has some connected components. So these are connected components. And each connected component is just a covering of the base. Yeah? So from here we have a projection to the base. And if we look at this and the restriction to one of the connected components, then it's a covering. Of the base. Now, we should consider, yes, so these points correspond to the points in one of these connected components. So we need now to look at the points of the connected components that also lie in the corresponding degree of the Hodge filtration. So let's look at the total space of our bundle Fk now. So the total space of the bundle Fkv is the submanifold inside the total space of V. So we may take this component and consider the intersection. with the total space of FKV. Then there are two possibilities, actually. So it may happen that two possibilities. So it may happen that this entire submanifold Wi is inside this total space of FKV, so that all points in this component are of type KK. Yeah. So this condition here. So equivalently, we may write that X is in VKK, yeah, intersected with VBT. So this T here. FKV intersected with FKV bar is this bundle VKK. And it may happen that all the points in Wi are inside FKV. So then Zi equals Wi. And then the projection of this Zi equals B. So this component is dominating. This Zi is a sub-variety inside V. Yeah, so this Zi is a complex, closed complex sub-variety. Of the total space of V. It may coincide with this component, then this Zi is called dominating. Or it is strictly smaller. It may be reducible, so Zi is not necessarily irreducible. Yeah? So it may be reducible, may have several irreducible components. But then each of them is strictly smaller than this Wi. So the dimension then will be, or the dimension of Zi is smaller than the dimension of Wi, and which is the same thing as the dimension of B. And then the projection of Zi, so if it is a submanifold inside of this space of smaller dimensions than the dimension of B, then the projection, it will be, at least we may claim that it is nowhere dense. Relatively a small subset of B. And so this subset means, so if we are in the image of Zi under the projection, then this means that we have in these points of this image, we have some Hodge classes that do not survive over all points of the variation of Hodge structure. So the points of this Zi correspond to Hodge classes that do not deform in all directions along B. And then we take the union of all such components. So there is a countable number of connected components here, and we take the union, or more precisely, not only for this one local system, we should take the union for all of its tensor powers. So we apply this tensor construction and somehow take all these components that are non-dominating, take their union. It will be some subset which is still nowhere dense in B. No, it's so sorry. So this will be somehow, it's a countable union of subsets that are nowhere dense. It may be dense, and it will be actually in most of the cases. But still, it is not everything. Yeah, by Bayer theorem, this B may not be covered by a countable union of nowhere dense subsets. So let's write this down. Let's take now so let's write this like this. So B Hodge. So I want to define the Hodge locus. So this Hodge locus of this one VHS. So this is the union of the projections of all such components that are non-dominating, so that P of Zi is not equal to B. And then, okay, so let's put so this VB here. So let's denote it like this. And then the Hodge locus is so B Hodge is just the union of Hodge loci for all tensor powers. So T, E, F, VB. So this TEF, I recall, it is just the tensor power of B product with the tensor power of its dual. So we take all these tensor constructions and take the union of all these non-dominating components for all tensor powers. So this is the Hodge locus. So B is not equal to B Hodge, yeah, because B Hodge is a countable union of nowhere dense subsets. So well, in fact, we can say more than this about the Hodge locus, not just that they are a countable union, not that it is a countable union of nowhere dense subsets, but also these projections actually, so P of Zi, they are closed subvarieties of the base. So let's prove this. So that is where I stopped last time, I think. So how to prove that the image of Zi is a closed subvariety of B? So you see the projection P is not a proper map. So if we have something closed inside the total space of V, it need not a priori be closed in B. But in fact, the projections of Zi will be closed. So let's prove this. So this is a proposition. That for any I, the restriction of the projection to this Zi, so it goes from Zi to B, is a proper map. In particular, the images of Zi are closed analytic subvarieties. Yeah, so in both cases, actually, both in the case when this Zi is equal to Wi and when it is strictly smaller, it will be always, this restriction will always be a proper map. So how to prove this? Let's recall that we have a polarization. And if we have some point in Zi, then this corresponds to a Hodge class. Yeah? So this point is actually an integral class of type kk. Yeah, well, let's assume again that we are in weight 2k again. Let's compute the norm of the class corresponding to this point using the our quadratic form Q. But know that actually, well, let's define A to be, well, let's just say 2 pi I psi of x. So what I want to note here is that this is actually the same thing as q of x. So why? Because we have, so the difference is the value operator, right? So in principle, I should put c here. But x is of type kk, so the value operator acts as the identity here. So this is because x is of type kk. So cx equals x. And well, this is greater or equal than 0, and 0 if and only if x is equal to 0, right? So this is some non-negative constant. Also, note that well, I have chosen some point in this subvariety zi, but I want to so here is k. So I want to say that actually this constant does not depend on the choice of the point in this subvariety zi. So a does not depend on the choice of x in zi. Why? So let's recall the definition. So this zi was in the intersection of some connected component of the local system. Yeah, so wi. So this means that the points of zi are obtained, so one from another by parallel transport, yeah, along our flat connection. So this wi, somehow the local sections of this somehow the points of wi correspond to different to results of the parallel transport along different paths on the base. So this wi is a connected component. That's exactly what the connected component of the total space of this local system is. So one is obtained from the other by parallel transport. But this psi, so this thing, so it's actually I have erased, but this psi was actually a morphism of local systems. So because so I'll just write that nabla psi is 0. Yeah, so psi is flat. So this psi is preserved. So the value of this thing is preserved under parallel transport using the flat connection. And so the value of a does not depend on which point we have chosen in this subvariety zi. So zi is actually contained in the inside the set of all kk classes of norm, well, equal to a or less or equal to a if you want. So let's define this set. So it's a kind of a sphere bundle or a ball bundle. Well, let it be a sphere bundle. So SA. So let's take all the points in VK. Well, let's say in the total space of VKK. Yeah. So all classes of type kk such that q of z bar is equal to a. Okay. So this is a complex vector bundle, and q was positive definite on the real, somehow this complex vector bundle, the complexification of a real one. And so Q was positive symmetric on this real bundle. So it defines a Hermitian form on VKK. So this is just a sphere bundle. So SA over B is a sphere bundle. So let's denote this P restricted to SA is a sphere bundle So the spheres are compact, so this is a proper map. But Zi, as we have observed here, is inside SA. Okay? It's a closed, so this is a closed subset. And so the restriction to Zi is also a proper map. It follows from here. So it follows that the restriction to Zi is also a proper map. Okay, so a proper map, yeah, so I recall if I haven't spelled this out. A proper means that the preimage of a compact set is compact. Okay, so the preimage of a compact set in B here in this sphere bundle is compact, and then the intersection with a closed subset is also compact. That's the proof of the proposition. So we see that actually we get a countable union here of here. So this is a countable union of some closed complex subvarieties. Well, I have to make this remark actually because that is one of the central results actually of Hodge theory. So in some particular case, when the case that is maybe most interesting is when actually this variation of Hodge structures is over something algebraic. So in the case when B is algebraic, well, let's say quasi-projective. So remark, when B is quasi-projective, so these subvarieties are not only closed, they are also algebraic. So P of Zi is algebraic. So this is a theorem of Catania, Dillin, Kaplan. And then the Hodge locus is a countable union of algebraic subvarieties. But this, I will not, I think, explain this, but just state it as,
How do you see that I is closed in SA?
So it was a closed subvariety in this total space, but it was actually contained in SA. So why it is closed subvariety? Because it's an intersection of two closed submanifolds, actually. Yeah. So WI was a closed submanifold in the total space of my complex vector bundle, holomorphic vector bundle. And the total space of a subbundle is also a closed submanifold inside the total space. Yeah? So it is closed in here, but actually the projection is also closed. Okay? Yeah, please, more questions. So this is the Hodge locus. So we were discussing actually the Mumford-Tate groups. So the goal of introducing this Hodge locus, well, actually it is interesting in its own, but we are discussing the Mumford-Tate group. So what does it tell us about the Mumford-Tate group of the variation of our Hodge structures? So the Hodge locus is somehow the union of all these guys that project non-dominantly onto the base. So what happens with these guys that somehow project dominantly onto the base? So let's think now about this case when the WI, so this entire connected component, is of type KK. So it defines Hodge classes over all points of B. So let's look at this Hodge class. So actually, so let's just define a subvariation of Hodge structures given by all such components that project dominantly. Let's observe that, well, if this WI is equal to ZI, Then, Wi was somehow a multi-section of the local system. So it spans a sub-local system. Then Wi spans a sub-local system of our local system that carries the variation of Hodge structure, so that this sub-local system that is in VKK, yeah, so that is entirely of type KK over all points of B. And if we have two such sub-local systems, then their sum obviously also has this property. Yeah, so we can consider the biggest such sub-local system inside our VHS, which is purely of type KK. So Hodge Tate. Yeah, so purely of type KK, we call this Hodge Tate. So let's define it. So the definition is that VB. Well, I'll just write it like this. This is Hodge Tate. Somehow the maximum, the biggest is the biggest sub-local system in VB. That is Hodge Tate. So that is of type KK. And then, so this somehow is the complement of our, somehow these classes survive everywhere, over all points of the base. The Hodge classes corresponding to the points of this sublocal system. And then, about the Mumford-Tate group. So let's recall that the Mumford-Tate group is actually defined as, it is defined as the smallest algebraic Q subgroup that contains the image of the Deligne torus, but we know that we may also say that the Mumford-Tate group is just a stabilizer of all 0, Hodge classes in all tens of powers of V. If V is our Hodge structure. So somehow Mumford-Tate group should stabilize, the Mumford-Tate groups of the fibers should stabilize all Hodge classes in this sublocal system. So the Mumford-Tate group should always be contained in the stabilizer of all the classes here. Actually, that is that is the generic, so to say, Mumford-Tate group. So over the complement of the Hodge locus, the only Hodge classes in all tens of powers are only these sections, somehow the points of this sublocal system of Hodge Tate type. These classes exactly are the classes that define the generic Mumford-Tate group. But one other thing, so I'll define this generic Mumford-Tate group in a few minutes. So first I want to prove something about it. The statement is the following. So let's fix one point in the complement of the Hodge locus. So let's say we have a point in B minus B Hodge in the complement of the Hodge locus, which is non-empty. Let's say, MT with index T is the Mumford-Tate group of the corresponding Hodge structure. So the Hodge structure here is on the fiber of this local system. Given by this filtration on the corresponding fiber. So this is the Mumford-Tate group. Also, we have the monodromy representation of the base. So we have our local system. And if we do parallel transports along the loops based in this point T, well, let's call, okay, let's actually call this base point. So this is a base point, we'll call it T0. Yeah, so the parallel transport along the loops with base T0 defines an action of the fundamental group of B. So we have the monodromy action, the monodromy representation. Let's call it mu, pi 1 of the base into, actually it preserves some quadratic form given by the polarization, but maybe that is not so important right now. So let's just write GL of this VB T0. Yeah, so it acts as automorphisms of this fiber. All right, actually the claim is that I want to prove proposition. So in this setting, if we have a point in the complement of the Hodge locus, the Mumford-Tate group at T0 contains a finite index subgroup of the image of the monodromy representation. Okay, so, well, so why is this? The proof. Well, like I said, so the Mumford-Tate group is a stabilizer of all Hodge classes, 0, 0 Hodge classes in all tensor powers. So the stabilizer of all 0, 0 Hodge classes in somehow the tensor algebra of this Hodge structure at point T0. And so since, yeah, so let's observe first that actually, well, it stabilizes all of them, but it's actually an algebraic group of finite type. So if we consider, so these Hodge classes, they form a countable set. And if we somehow consider them one by one and look at their stabilizers and start intersecting them, then this process should stop after a finite number of steps, because it's an algebraic variety of finite type. So actually we may find a finite number of Hodge classes that are already enough. So it is an intersection of stabilizers of several Hodge 0, 0 Hodge classes. So there exist these Hodge classes xj. So let's say they are in T Ej Fj of V B point T0, yeah, and the intersection with F0, let's say T Ej Fj V 0, 0 at point T0, yeah, like this. Such that, so J goes from 1 to some M, such that the Mumford-Tate at T0 is the intersection of the stabilizers of Xj. But now notice the following. This thing, so this set of Hodge classes, it is over the point T0, and our point T0 was in the complement of the Hodge locus. So T0 does not belong to the Hodge locus. What does it mean? So this means that all our Hodge classes actually they survive over over this point T0. So the Hodge classes over the point T0 are all contained here, actually. So they all survive under any somehow arbitrary deformation somehow. When we move from the neighboring points, so all these classes stay also Hodge. Yeah. So if we do the parallel translation of these classes to a neighborhood of T0, they still stay Hodge. So in other words, so this xj actually is in the somehow Hodge Tate sub-local system of this tensor power. So we have this tensor power of VB, and then we have this Hodge Tate sub-local system in the tensor power. Well, and the point T0 here. Okay. But now, so this thing now is a sub-local system. So these xj's are just some somehow elements in one of the fibers. But we have the monodromy group action on this local system, this Hodge Tate local system. And notice that this Hodge Tate local system, so all these points of type kk under all overall points of the base. Pi1 of B so acts on the fiber of this Hodge Tate local system at T0. But notice that the previous proposition, so in the previous proposition, we have proven that so if we have this xj, so it will lie in one such connected component in the total space of the local system. But since this entire connected component is of type kk, actually, so the map, the restriction of the projection to the base from this connected component is a proper map. So by the previous proposition, actually, the orbits of this action are finite. So why? Well, because somehow this local system, so the fiber of this local system is a lattice inside the vector space. And the projection, somehow we have shown that all the images of these xj's under the monodromy action, they have the same Hodge norm, the same norm defined by the polarization. Yeah, so and the projection from this sphere, so the polarization defines a compact sphere, like in the proof of the previous proposition. And so these points of the lattice are contained in the sphere of some finite radius. So there are only finitely many such points. So every point has a finite orbit under this action. So by the previous proposition, so all xj's have finite pi1 of B T0 orbits. And then some finite index subgroup of this pi1 stabilizes all xj's. So there exists a finite index subgroup of pi1 of B T0 that stabilizes all xj's. So know that since there are only finitely many of them, yeah, so we can always find a finite index subgroup here. So each xj has a finite orbit, and so we can find a finite index subgroup in this group that stabilizes all of them. And then this finite index subgroup, it is contained, so this subgroup its image, or more precisely, the image of this subgroup under the monodromy representation will be contained in the Mumford-Tate group, because the Mumford-Tate group is exactly the intersection of all stabilizers. So this subgroup maps to the Mumford-Tate group of the corresponding Hodge structure by mu, by the monodromy representation. And so that that gives us this conclusion. Okay, so the Mumford-Tate group contains a finite index subgroup of this image. One may also define the algebraic monodromy group as the Zariski closure of the image of this monodromy representation inside this general linear group. And then the proposition actually says that the connected component of this algebraic monodromy group is actually equal to this generic Mumford-Tate group. Okay? So yeah, so that's our proposition. So I will use it in a minute. Yeah, so why do I need this proposition? Well, I need this proposition actually because sometimes we can consider families, and we know something about the monodromy action on cohomology in these families. And they actually, so that is the proposition that lets us somehow conclude something about the Mumford-Tate group. Actually, sometimes we can prove that this Mumford-Tate group is big because it contains the image of the monodromy representation, and the monodromy representation is sometimes quite a big subgroup inside this GLV. Yeah, so to somehow to apply this, well, let's first write down this definition. So I have already said it, but now, so let's just write this down. What is this generic Mumford-Tate group? Yeah, so the generic Mumford-Tate group is essentially this. So the Mumford-Tate group over any point in the complement of the Hodge locus. So how it doesn't really essentially depend on the point because, well, so this Mumford-Tate group is just a stabilizer of all classes in this Hodge-Tate sub-local systems. So we have the local system somehow of algebraic groups defined as stabilizers of all classes in all tensor powers of these Hodge-Tate type sublocal systems. So let's write this down. So if we, well, just take any point in B and define the group GT as the intersection of all stabilizers of X, where X is in this Hodge-Tate type sublocal system in the tensor algebra, yeah, over the point T, right? So then this GT form, form a local system of algebraic groups. And actually, so we may identify over the different points, we may identify these groups by parallel translation. And a fiber of arbitrary point is called the generic Mumford-Tate group. So a local system of algebraic groups, let's just call the fiber with fiber G, and this G is called the generic Mumford-Tate group. So the generic Mumford-Tate group. So for any T in the complement of the Hodge locus, GT is equal to the Mumford-Tate group over the point T. And for all points in the Hodge locus, we have the Mumford-Tate group is contained in GT. Yeah. So the Mumford-Tate group should always stabilize all the Hodge classes of this somehow Hodge-Tate sublocal system. But over the Hodge locus, we have more Hodge classes. So this intersection of the stabilizers will be smaller in general than the GT. But over the very general point, we have this equality. Yeah, so the what's very general point actually for us will mean exactly this, that we are over the complement of the Hodge locus. Okay, so any questions to this part? About the monodromy and the generic Mumford-Tate group. So that's actually maybe even the key, somehow the key point of our discussion. Which actually, because it allows us in some cases to find the Mumford-Tate group or to prove that somehow the Mumford-Tate group for a generic member of some family of varieties is as big as possible, let's say. So let's have a look at an example. So actually, somehow examples depend on the computation of the monodromy group, which is, I think, a topic, a little bit different topic. So how to find the monodromy group is a separate question, and it uses the Lefschetz theory, the theory of Lefschetz pencils. But I think I won't tell you too much about this, but just state somehow what we know about the monodromy of the families of, let's say, hypersurfaces in Pn. So let's consider an example, a hypersurface of odd degree in Pn. So that's an example that I would like to mention. So example. So the base of this base B will be the space of smooth hypersurfaces in CP n of degree d. Well, what is this space? So the hypersurface is given by a polynomial of degree d. Yeah? So then this B is an open subset in some projective space also. CP, well, of some dimension given by some binomial coefficient. I guess like this. So open, Zariski open subset. The complement to the discriminant. Well, anyway, so the important thing is that it's a quasi-projective variety, yeah, so that all these theorems actually, and we have a universal family of our hypersurfaces. So pi from X to B is a universal family. So here, all these theorems apply. Actually, the Hodge locus is the countable union of algebraic subvarieties. So let's look at the Mumford-Tate group of a very general hypersurface. Well, I want to assume that, well, it's not really so important, but just to give an example, I want to assume that the hypersurface is of odd degree. So assume that n is even, yeah, so then the dimension of x is odd, and then the somehow middle cohomology of x. So the middle cohomology of x has a polarization which is skew symmetric. Yeah, so the middle cohomology of x is in degree 2r minus 1, and it has a polarization which is a symplectic form on this space. So let's okay. So let's better denote. So we have our variation of Hodge structures over B. So that is the high direct image of the constant sheaf on the universal family. So this is the variation of Hodge structures over B with the fiber which is the middle cohomology of our hypersurface, and the polarization psi is skew symmetric. So it's just given by the intersection product in this case. So it's skew symmetric, and then actually the monodromy representation it goes into the symplectic group. Yeah, so the symplectic group of one of the fibers. The theorem here is that this the image of mu so the theorem is attributed to Kazhdan and Margulis. But it's actually just the application of the Lefschetz theory of Lefschetz pencils. So one needs to find enough somehow SIMP, which will be the risky dense in the corresponding algebraic group. So the image of mu is the risky dense in this corresponding Q algebraic group. And so the corollary, what can we conclude from here? So we know that so this image, some finite index subgroup of this image is actually contained in the Mumford-Tate group. But then the finite index subgroup will also have a Zariski dense image. So we may actually conclude that this Mumford-Tate group, that the generic Mumford-Tate group the generic Mumford-Tate group will not be this SP, yeah, because SP it will be SP plus the center. So let's better phrase the corollary in terms of the Hodge group. Yeah, so about the Hodge group we may state all the same things. We have this variation of Hodge structures of fixed weight. Yeah, so the action of the center that defines the weight is not really important here. So we may talk about the Hodge group. So the corollary is that the generic Hodge group of the family X is SP. So this full symplectic group. Okay. So the conclusion is actually that the Hodge group is as big as possible. Yeah, so it cannot be bigger because it has to preserve the polarization. But it is exactly this symplectic group. The generic Hodge group of this family. So recall that we have discussed the Hodge decomposition on the Lie algebra of the Hodge group or the Mumford-Tate group. So let's have a look at what we can say about the Hodge decomposition on the Lie algebra in this case. For a very general, hypersurface, we know the Hodge group of the Hodge structure on its middle cohomology. So, for example, well, let's just assume that the hypersurfaces, well, the first, I guess, well, the example that I would like to consider is n equal to 4, d equal to p. Sorry, in P4. So a quintic threefold. Which is a Calabi-Yau variety. Okay, so the canonical bundle of X is trivial, and so we have on the middle cohomology we have the Hodge number H30 equal to 1. Yeah, so the global sections of the canonical bundle are just one-dimensional. And then actually one may compute the other Hodge numbers. It's not so important what they are. I think that H21 will be 101, and then symmetrically the other Hodge numbers. But what is important here is that, well, that we have this H30. Well, then, so we assume that this X is, X equals xt for t in the complement of the Hodge locus. Okay, so then we have that our Hodge group of the cohomology, the Hodge group of X is equal to the symplectic group H3 with the intersection product. So let's look at the Lie algebra. Well, Lie algebra of this Hodge group so what is it as a representation of this SP H3? The Lie algebra, so we have discussed Lie algebra of this orthogonal group, which was lambda 2 of this vector space. So here it will be actually isomorphic to the symmetric square of H3, well, with some twist, Hodge-Tate twist. So let's compute the Hodge numbers here. So the symmetric square of H30 will give you a Hodge component of type 60, and then you add this Tate twist, so this will be Hodge types on this guy. So this will be 3 minus 3. Then the product of H30 and H21 will be of Hodge type 5, 1. So minus 3 will give you 2 minus 2. Yeah, and so on. So we'll have in this Hodge structure, we'll have Hodge type 3 minus 3, 2 minus 2, then 1 minus 1, 0, 0, and up to minus 3, 3. Yeah, so all of them. Not only this type 1, minus 1, 0, 0, and minus 1, 1, which we have discussed before, but also more components. So we have seen that this means that the Hodge structure is not abelian. Yeah, so this means that H3 of X with rational coefficients does not belong to the category of rational Hodge structures of abelian type. So it is not generated by the, it's not in the subcategory generated by the abelian varieties in this example. Yeah, of this hypersurface. Also, we can consider hypersurfaces of even degree. So, for example, we have seen, we have computed before the Hodge structures on the H2 of a surface in P3. And we've seen that if the surface is of degree at least 5, then also the Hodge structure on the Lie algebra of the orthogonal group is not of abelian type. It contains more Hodge components. And then, so this theorem actually, so it also will work in the even case. And then you can conclude that for a very general surface in P3 of degree at least 5, also the generic, so the Hodge group will be equal to the full orthogonal group. And then the conclusion is that the Hodge structure is not abelian. Okay. Well, so this is the story about this examples of non-abelian Hodge structure. So we have actually, we know that there exist some varieties at least that with cohomology of non-abelian type. Okay, guys, so questions, comments? Huh? The Kazhdan Margul, I don't think so, no. But yeah, so yeah, I was, because, sorry? So I wanted to talk rather about the period domains. I think I won't have time to explain the proof of this Kazhdan-Margulis, but the idea is actually to use Lefschetz pencils. So you just look at the Lefschetz pencils and look at the monodromy action, which is given by some reflection, yeah, by the symplectic reflection. And then the idea is that you should prove that there are enough of these reflections to generate some subgroup which will be Zariski dense. Okay, so yeah, so to conclude today, so I want to to conclude this part of the story. Yeah, so with the variations of Hodge structure. Huh?
So it makes sense only for middle cohomology.
Yes.
And then why do you write this quote? I mean, it's also true for
right.
for orthogonal.
Yeah, right. So this will be true for the orthogonal. Just to give an example, it's just an example. Yeah, so that's true. So in the orthogonal case, you should just replace this with the orthogonal group. In the even case, you should just replace with the orthogonal group. Yeah. So this Kazhdan-Margulis is okay. The Lin claims that it is Kazhdan-Margulis, and then yes, there is a proof in the book of Freitag-Kiel about the Tal cohomology, also attributed to Kazhdan-Margulis. So I think so. Yes. Huh? So Freitag-Kiel Eladic cohomology, I think. Yeah. And Delin, yes. So yeah, I should mention actually that. So what I was talking about today. So this claim about the properness, yeah, of the map of the Hodge loci are somehow unions of closed subvarieties, and especially this thing that the generic Mumford Tate group contains some finite index subgroup of the monodromy. So this is due to Delin. So this is in his paper about the Weil conjectures for K3 surfaces. Okay, so this was in the old paper of Delin. Good. So yeah. So just to conclude this story with the VHS, of course. So I have mentioned maybe before that what we want actually is to somehow to produce some classifying spaces for variations of Hodge structures. So let's say we have this VHS over the base, but actually this VHS is just a collection, is a bundle with a flat structure, with a flat connection, and with a flag of subbundles. So this is somehow a linear algebraic data. So the flags are classified by the flag variety, right? So essentially the classifying space for the Hodge structure should be something like a flag variety, basically, with some caveats, because that is essentially what it is. The variation of Hodge structures is just a bundle with holomorphic subbundles. Indeed, so one may construct the somehow the classifying spaces in some sense. So they're called period domains. So let's just talk today about the period domains and period maps. And I will try to yeah, so my goal is just to explain again. So I'm somehow focusing on this distinction between abelian and non-abelian Hodge structures. Yeah, so like in this example, so here we have a non-abelian Hodge structures. On abelian varieties, we have abelian Hodge structures. So I want to try to at least mention so what it means on the level of the classifying spaces, actually, because this condition that the Hodge type on the Lie algebra has only components of type 1, -1, 0, 0, and -1, 1. So this has some meaning also for the period domain. So let's talk about the period domains a little bit. So we have our local system, over B. Well, we may actually, if we want to construct it as a pullback of some universal family over some classifying space, it's better to first to assume that B is simply connected, or to pass to the universal covering. So let's pass to the universal covering. And so we have this pullback. So this is a trivial local system. So let's say this is just some free Z modulo finite tensor with the trivial local system over the universal covering. So this V is just that R. And then we have the, so we have our vector bundle, which is just V tensor product with the structure sheaf of this B tilde. And then we have a bunch of subbundles, Fp, V, inside V. So they form a flag. And also we have our polarization, psi. What we know is that we are in the following situation, that over this B and over B tilde, we have the, so for a very general point, we have a generic Mumford-Tate group. So let's denote it by G. So T0 is in the complement of the Hodge locus. So the Mumford-Tate group of our Hodge structure is G. So this is a generic Mumford-Tate group. So this means that actually our Hodge structures, they are given by a representation of the lintors in this G. So let's better talk about the representation of the unit circle. So we have, so let's say, so this is of fixed weight. So local system and the Hodge structure is of weight K. So we may restrict to the unit circle and look at the representation into this group G to the Lie group of its R points. So G is, well, so let's write the Hodge group here. Hodge group, so the generic Hodge group, which is a reductive group, right? So as we have discussed, reductive group. And our Hodge structures are just given by, if we fix the weight, and if we fix the type of the Hodge structure, if we fix one such representation, then the other Hodge structures on the neighboring fibers are given by somehow continuously deforming this morphism of real algebraic groups, right? So the classifying space of the Hodge structures should be just, well, a connected component. So let's define this classifying space as follows. So the definition D is the connected component of of this space of homomorphisms from U1 to GR containing rho 0. So we start from this point. We have this generic Hodge group. We fix this group. And then on the neighboring fibers, the Mumford-Tate groups, they may become smaller, but still, as I have said, so the Hodge group will always be contained in this G. So on the neighboring fibers, the Hodge structures are given by deforming this morphism of algebraic groups. So how to deform a morphism of algebraic groups? Actually, so here is a useful statement. So the claim is actually that all these deformations are given by conjugation. So D is actually isomorphic to, it's a homogeneous space. So if we act on this space by conjugation, so this will be a G of R the connected component module is a stabilizer of rho 0, where G of R acts on this space home by conjugation. So the action, so if we have some element here, so G dot rho 0 at some point Z, so this G dot rho 0 is a representation of the circle. At this point Z, this will be, so G rho 0 of Z, so G times rho 0 of Z times G inverse, so it acts by the conjugation on the image. So I'll just briefly sketch the proof. So why is this actually true? So the idea, because so this is a structure theory of reductive groups essentially. So the proof is it goes as follows roughly. If our so if we look at the image of this rho 0, it's a compact abelian subgroup in G of R. Is a compact. It's a unit of the circle, the compact abelian subgroup of G of R. So it is contained in the in a maximal compact torus in G of R. Well, actually, we can even write this connected component. So this 0 just means that I take the connected component of this thing as a Lie group, because actually G is connected as an algebraic group, but the Lie group may have some connected components, so that's not really so important now. So the idea is the following. So we have this image of rho 0 inside G of R, and it is essentially some one-dimensional subgroup inside the maximal compact torus. But then all maximal compact tora are conjugated by the action of this guy. So this is somehow the fact about the reductive groups. So since this G is reductive, and so all maximal compact tori are conjugate by the action of this connected component. Okay, so if we are given some other representation of U1, that corresponds such that the point, this row, is in D. Yeah. So if we consider this space, and if we consider another point inside the same connected component of this space, so it is also contained in some maximal torus, right? So let's fix one such maximal torus that contains this row 0. So let's call this torus T0. So image of row 0 is contained in T0. So the other maximal torus will be conjugate to this T0. So from this fact, it follows that there exists some element in the group, which is a connected Lie group here. Yeah. So there is some element such that G dot row is contained in the torus T0. Okay. So this G dot row is also a point in the same D. So this G dot row is also a point in D. So we get 2 points of D that correspond to that lie in the same torus T0, fixed maximal compact torus. But then what are these subgroups? What are the homomorphisms from U1 to the compact torus? So these are co-characters, right? So they're called co-characters. And somehow, so they form a discrete set. So the homomorphisms from a circle to a compact torus, which is a product of circles. So the space of such homomorphisms is a discrete set. So let's say, so this hom from U1 to T0 is a discrete topological space. But now we have obtained 2 points in this discrete space that lie in the same connected component. So they actually should be this. So they should be the same point actually. So. Well, then this G dot row is equal to row 0, but that is exactly what was somehow claimed, right? So that this D, well, of course, yeah. So if we act by conjugation, we get the points of D, but actually every point of D can be obtained by this action, yeah. So from row 0, so the row, you may rewrite this, claiming that row equals G inverse dot row 0. So the action is transitive. So actually, all such Hodge structures are obtained by somehow acting by this group by conjugation. And so this is the description of our space as the homogeneous space. Now, so what can we say about this homogeneous space? Let's look at this somehow, at this description. So let's call this stabilizer K. So let's say that K is the stabilizer of this fixed representation, yeah, that gives the Hodge structure over the base point. Well, what can we say about the stabilizer? So I want to say that the stabilizer is a compact subgroup. So why is it a compact subgroup? Let's recall that we have the veil operator, right? So we may consider row 0 of I. So this veil operator and the adjoint action of this veil operator, we have discussed it. So this is the Cartan involution. On G of R. We have seen this. What does it mean that it is a Cartan involution? It means that the somehow twisted real form of this G of R that I denoted by G sigma. So what is it? So it's this just a group of all complex points of G such that G bar equals sigma of G. So the claim that this sigma is a Cartan involution means that this group is compact. So this group is compact, which we have seen. But now, what about the K? What about K? So if we have a point, so if this Z is a point in K, then sigma of Z is equal to, oh, sorry, so this was G. If G is a point of K, then sigma of G equals G. Why? Because so what is the stabilizer? The stabilizer somehow is a stabilizer under conjugation, right? So it is a centralizer. That's the set of all elements of this group that commute with the image of row 0. And the Veil operator is in the image by definition. So K commutes with this Veil operator. So the sigma acts as the identity on K. So sigma restricted to K is the identity. Okay, that's just the definition. So from here it follows that K is inside G sigma, right? Because K is a real group. It's inside this real Lie group, so this G of R. So G bar equals sigma of G for any G in K. Okay, so K is compact. Good. So that's one thing. What we'll have? We have a quotient of some connected real Lie group by a compact subgroup. So we may, for example, immediately introduce some Riemannian metric, homogeneous. It's a homogeneous space. It has a homogeneous Riemannian metric, which we will introduce in a few minutes. Before we do that, let's also observe that we have a complex structure in this space. So I would like to, so there are several ways to explain the complex structure. Let me explain that actually, so this D may be realized as a subset of some projective manifold, open subset of some projective manifold. The flag variety, actually, the manifold that classifies, parameterizes the collection of these flags. So a flag in a fixed complex subspace with some fixed dimensions. Yeah. How does this work? So let's see the Lie algebra of our G. So we have this Hodge decomposition on the Lie algebra of G. And so let's think about the meaning of different somehow Hodge components in this decomposition. So G is the Lie algebra of this GR. Okay, so let's say G. So we may consider the corresponding, so G is defined over Q. So this is a rational Lie algebra. But now in GC we have the Hodge decomposition. It's a sum of components of type P minus P. So it is of weight 0. The Hodge decomposition with respect to which Hodge structure? With respect to the Hodge structure given by this row 0. Yeah. So the Hodge decomposition with respect to the Hodge structure given or induced by this row 0. Yeah, so this base point in our space. So what's the meaning of different components? So we know that somehow row 0 of Z restricted to this G P minus P. So what is it? It's a multiplication by Z to the power p times z bar to the power minus p. But z bar, so if z is in the unit circle, then z bar is equal to the inverse. So z bar is equal to z inverse, and then this will sum up to 2p, right? 2p times the identity. So on all components, it acts non-trivially apart from the component of type 0, 0. So G0, 0 actually. So what does it mean? That on the component G0, 0, it acts trivially. So this component is exactly somehow the subspace in the Lie algebra that commutes with the adjoint action, of row 0. So this is exactly actually the Lie algebra of the stabilizer of row 0. Or more precisely, if I intersect this G0, 0 with the real part, so this will be the Lie algebra of the stabilizer. Okay, so the tangent space now to D is just the quotient of this the real somehow the intersection of this with the real part by the 0, 0 component. Well, let's consider a different homogeneous space. Okay, so let me leave this here. So I now want to look at the filtration, at the Hodge filtration. So let's look at the Hodge filtration. So the Hodge filtration on GC also. So how this is defined? So this is the direct sum of all R greater or equal than P of G R minus R. And let me take F0 of GC. So what is F0 of GC? Well, this is the Lie algebra somehow of the this Lie algebra first of all, indeed, this is Lie subalgebra, right? So because when we take the bracket, so the we should so if the bracket of two elements, the Hodge types are additive with respect to the Lie bracket. So this is a Lie subalgebra that corresponds to what? So the meaning of this by degree is that if you act by an element of this by degree R minus R on the vector space, the original vector space that carries the Hodge structure, yeah. So the vector space, so this G of R was inside GL of V tensor R, right? So this V was over the point T0. So if we act on the component of by degree PQ in this vector space, then the Hodge type is also additive. So it will increase the first Hodge index by R and decrease the second by R also. So then this F0 of GC is the Lie subalgebra that well, it will increase or it will non-decrease the first index, right? So this means that it will preserve the Hodge filtration. On V, the Hodge filtration, so that it will map, yeah, so the elements of bracket with the elements of this F0 will map FPV into FPV for any P, okay? Okay, so then we may consider the corresponding subgroup of the complex Lie group. So then let P be the group such that the Lie algebra of this guy is F0 of GC. So then, so define, let's give the definition. So D hat is the quotient of G of C by this group P. So this is a dual, somehow the dual of D, the dual homogeneous space. So what's the relation between D and D hat? The relation is that one can be embedded as an open subset of the other. So this D hat is the quotient of G of C by this P. So what is P? P is the subgroup somehow with Lie algebra F0G. So this is a subgroup that stabilizes the flag. So P is a stabilizer of the Hodge filtration. On this V B T0 tensor C, right? So this is such a parabolic subgroup, and D hat is a projective variety, actually. So this is a flag variety. Well, the partial flag variety. So flag variety. So this group G of C will act on this space of all the filtrations on this complex vector space, right? So the P. Sorry.
Just a stupid question.
Yeah.
So F0 of GC
Mm-hmm.
is the sum over all R greater or equal than 0 of G R minus R.
Mm-hmm.
But this is G itself, no?
No, so you have in G, so it's somehow symmetric. So you have G0, 0, G1 minus 1. So here you have G minus 1, 1, and somehow this may go on. Yeah. So this G0, 0 part, if you if you intersect it with the real Lie algebra, then this will be exactly the Lie algebra of the stabilizer of rho 0, as we have observed, right? And now I want, instead of this, I want to somehow look at the whole somehow sub-algebra that is somehow to the right in this picture. And the quotient is a homogeneous space. So the observation is that this sub-algebra corresponds to a group that stabilizes the Hodge filtration just as a flag of subspaces. So this D hat is a flag variety, so the homogeneous space of all flags in this vector space, law of flags of the given type, so to say. So the dimensions of these subspaces are fixed. Okay, yeah, I guess I should, yeah, so I will somehow get to some point now, and then I guess I'll conclude this discussion next time. So let me just finish, so let me at least explain how to embed this D into D hat. To embed it, it's easy. We just act on the base point of this D hat by the real Lie group. Yeah, so this is a homogeneous space for the complex Lie group. But let's act on this base point by the real points of this Lie group. And the orbit will be exactly D. So why is this? Well, just because somehow when we act, so what do we have to figure out? We have to somehow find the stabilizer of this point under the action of the real Lie group. So, or that this means that we should find the intersection of this P with the real Lie group. So the intersection of P with the real Lie group. Oh, well, let's bet on the level of Lie algebras, it's easier to understand, yeah? So the Lie of P intersection with the Lie of G of R. Yeah, so this is F0 of GC intersected with just the GR, right? So we look at this F0, so the sum of all these subspaces with the first index greater or equal to 0. And then we look at the real part. So the subspaces, so these two guys are complex conjugate. So inside this sum, the only real points are inside G00. So the intersection will be exactly this. So this is the same as G00 intersected with GR. which is the Lie algebra of K. Okay, so well, this means that let somehow us look at the base point corresponding to the identity element of the group in this D check. Yeah, so let's call this point somehow Z0, I guess. X0. Okay, X0. Well, let's consider the GR orbit of this point X0 is D, which is G of R0 into modulo K. Yeah. So this gives an embedding of D inside D hat as an open subset. Why is it an open subset actually? So, this we can prove by just computing the dimensions. Actually, let's compare the dimensions of D and D hat. So D is a real somehow homogeneous space. So the dimension of D is so let's write it here. So the dimension, the real dimension of D, is what? Is the real dimension of G minus the dimension of this thing. The real dimension of G00 intersected with GR, which is the same thing as, let's say this is the same thing as the complex dimension of GC minus the complex dimension of G00, okay? If we remove 00 from here, then what remains is twice the complex dimension of the sum of these guys here, because somehow if we remove 00 from here, then what remains is symmetric, so these spaces are conjugates of one another. And so this is twice the dimension of this thing, the dimension of the direct sum of G R minus R, where R is strictly less than 0, okay? Which is exactly, so what is this now? So this is the dimension of GC minus the dimension of P, right? So this is just twice the complex dimension of D hat, okay? So the real dimension of D is equal to twice the complex dimension of D hat. So this means that, twice the complex dimension of D hat is the same thing as the real dimension of D hat. Correct? So the real dimensions of these varieties are the same. And we have an open embedding. So this D is inside D hat is an open embedding. Okay. So this is somehow this flag variety. It has several orbits of the action of the group of the real points. So those orbits are different. They correspond to different somehow types of Hodge structures. So if we fix one Hodge structure, then all its deformations are inside one of these connected components. Okay. So so questions. Comments? Yeah, I think, so let me just finish quickly because otherwise I'll have to recall everything next time. So, okay, so once again, so we have started from some variation of Hodge structures. With some fixed generic Mumford-Tate group. So this G was the generic Mumford-Tate group. So we know that on all fibers the or the generic Hodge group rather. So on all fibers, the Hodge groups of the Hodge structures are subgroups of the G of R, this G. And we have constructed this homogeneous space that parameterizes all Hodge structures that are deformations of the Hodge structure on the base on the central fiber, and with the Hodge group contained in this fixed group G. So if we think about the Hodge structures as filtrations of the complex vector space, so over this B tilde we have a flat bundle, through V tensor O B tilde and a filtration. So this is curly V, and on this bundle we have this filtration by holomorphic subbundles. If we view this such filtration, such flag of subbundles defines a point in this space D hat, right? So we get a period map. So let's call it P. So P from B tilde to D. Well, to D, but actually, since all this to D hat, yeah, a priori it is to D hat. But since our subbundles actually define Hodge structures, and we know that all the Hodge groups are inside G, we are actually landing always in this subspace D inside D hat. Okay? Now, so one other important thing. So what can we say about the condition of Griffith's transversality? So remember that somehow, so this was a flat bundle, and the flat connection maps Fp into Fp minus 1. But what is a flat connection? It's essentially the differential, somehow the action of the flat connection is the same thing as the action of the differential of this map of the period map P. So the Griffith's transversality condition may be restated as follows. So Griffith's transversality is the following condition. So how to understand that the differential of the map has this property of decreasing the index of this filtration by 1 at most. So it means that the differential of P goes from the tangent space of B tilde to the tangent space, not the entire tangent space of D hat, but to a subspace. So inside, how did we define? So what is the tangent space of D hat at the base point? It's just the quotient of the Lie algebra by the subalgebra. So now inside of this quotient, we have a quotient of this component, F minus 1. Yeah. So we may say that this is, so F minus 1 GC defines a subbundle, homogeneous subbundle of the tangent bundle of D hat, right? So if we take the quotient of this guy by F0 GC, then this will be the subspace of the tangent space of D hat at the point x0, this fixed base point. And then by the group action, we may define this subbundle. So let's denote this subbundle by H. So this homogeneous subbundle, let's denote it by H. So this is the horizontal subbundle. And this subbundle corresponds to this subspace in the Lie algebra, which is the somehow minus first component of the filtration, of the Hodge filtration. So our period map, so this is the condition that is equivalent to Griffith's transversality. So the differential will land in the pullback of this horizontal subbundle on this homogeneous space. Okay. So somehow now let's recall about our discussion of the abelian Hodge structure. So you remember that we have talked about the Hodge structures with the following condition. So if GC is equal to G1 or G minus 1, 1 plus G0, 0 plus G1 minus 1, then the F minus 1 of GC is equal to GC. So this component F minus 1 that defines the horizontal subbundle is equal to the entire Lie algebra. And then this H, this horizontal subbundle, is equal to the tangent bundle of the hat, right? So this Griffith's transversality condition is vacuous. So there is no, so it holds automatically. So Griffith's transversality holds automatically for any holomorphic map from well, the base to this D to the corresponding period domain. Yeah. So there is no condition. So if we have this subbundle, then this subbundle is actually defines some distribution. It is not integrable. Well, why is it not integrable? Just because if you take the bracket of two elements of this subspace, you'll get something of Hodge type minus 2, 2, right? Unless it is 0, it will give you something that is already not contained in this subbundle. So in general, it is not integrable. So it is, but in this case, when we do not have more components, then this is automatic. So we, so any holomorphic map will define a variation of Hodge structures by pulling back the universal variation of Hodge structures over this D. But actually, also, what we may claim in this case is that, so there is a proposition. So so in this setting, so if we have all this, what we have discussed before, and additionally, if we have this condition, so if star holds, then D is a Hermitian symmetric space. Okay. So it is a Hermitian symmetric space. So let's think, so why? It is not so difficult to understand why, actually. Well, we see that it is a complex manifold, yeah, as a submanifold of this D hat, which was a projective complex manifold, actually. So this is the complex structure. Well, Hermitian symmetric space means that we should also have a Hermitian metric. But this D is a quotient of this real D group by some compact subgroup. So in this situation, we can always take any Hermitian metric on this Lie algebra of this real Lie group, take its average with respect to the action. Huh? Yeah, you can use the polarization also. Yeah, yeah. So you do have this always. So you have the Hermitian metric whenever you have the quotient by the compact Lie, you don't even need the polarization. So you have this Hermitian metric, but then the condition is that it is a symmetric space. Yeah, so the condition is that at every point there should exist an isometry, holomorphic isometry that fixes this point, and acts as -1 on the tangent band, on the tangent space. So where is this isometry here? Well, this isometry is actually now given by the Weyl operator, by the adjoint action of the Weyl operator. So let me just write this down here. So the at C acts on G1 minus 1 as, so what is the action of the at C? So this at C is it's the action of the Weyl operator on the subspace of Hodge type. So 1 minus 1 I have written. So it will be the imaginary unit to the power 1. I have already erased. So you have the I to the power 1 times I conjugate to the power -1, which is I squared, which is -1. Okay? So it acts as -1 here, as -1 here, and as the identity here. But this is the stabilizer. So if you take the quotient on the tangent space of D, it will act as multiplication by -1. So on this, actually, on G1 minus 1 plus G minus 1 as -1 as minus the identity. Yeah, minus the identity. So this gives the symmetry. So this at C preserves the base point of D because it also commutes with the stabilizer of rho 0. So this at C lies in the image of the rho 0. So the stabilizer is exactly the centralizer of the image. So this at C commutes with the stabilizer of rho 0. So it will act as an isometry that also preserves the, so it will preserve the complex structure, it will preserve the homogeneous Riemannian metric, and it will act as a multiplication by -1 on the tangent space. So this at C gives a holomorphic isometry fixing this base point that I have called x0 in D, yeah, and acting, so let me finish here. So isometry fixing x0 and acting as minus the identity on the tangent space of D at x0, okay? So this is a condition that defines this Hermitian symmetric space. So here it is just given by the adjoint action of the Weyl operator of the original Hodge structure. Yeah, so note that actually it was important that we have only these two guys here. If we had G2 minus 2, so then this at C would act as the identity, right, on this subspace. So that's exactly where this breaks down. Also, it's not difficult to see that this symmetric space is of non-compact type. So there are different types of symmetric spaces. So this is a non-compact guy, and this D hat will be the compact dual, and we have this embedding of the non-compact one into the compact one. Well, right, so this also gives the connection with the Shimura varieties that I have mentioned before. So the quotient of this Hermitian symmetric domain by the action of some lattice in the Lie group will give you a quasi-projective variety. For the general variation of Hodge structures, this space will, it will admit, so this will not be an algebraic, so the quotients by the lattice action will not be algebraic. So one may prove that they will always have algebraic dimension strictly less than their dimension, unless this D was a Hermitian symmetric domain. Okay, so yeah, I think I should stop here. So any questions? So next week I'll sorry, not on Thursday, right? On Thursday I guess I'll just talk a bit about the Kuga-Satake construction.